Again, appreciate this opportunity to talk to everyone. I'm going to just first give a quick overview of our research center and whatnot. I work in a research center at the University of Tennessee called CURENT, but it's spelled with only one R. This was established in 2011, and we too are supposed to be having a 10-year anniversary or celebration, except our 10-year won't be until August. And mostly looking at we call it the grid of the future, meaning when there's a lot of renewables on the grid. So in addition to the University of Tennessee, we have RPI, Northeastern, Tuskegee, a lot of faculty and many students at all of these institutions. Here at the University of Tennessee, we've got 10 faculty, 5 in power systems and 5 in power electronics, and then a few other affiliated faculty that also work with us. We've got a lot of industry and government members, including 5 DOE national laboratories, EPRI, the National Rural Electric Co-ops, and Underwriters Lab are also members of our center. And our vision at CURENT is to look, as I mentioned, about the grid of the future where we have lots of renewables. And our renewables, we need to be able to get that energy from wherever that energy resource is to where the loads are. And typically that's far away because a lot of our wind is in the middle of the United States, and we don't really have a whole lot of wind in that, load in that area or population. Most of our population is in the east or the west coast, so we need things like high voltage AC lines and DC lines. And of course, a major part of what we do is to try to educate the next generation of folks and students. I'm trying to change from pen to laser pointer. There we go. One of the other parts of this research center that I work on is called a grid emulation hardware test bed. Basically, we're using power electronics to act as load or generation or transmission lines. We can program these converters such that their behavior would be similar to a synchronous generator, or similar to an induction motor, or similar to a wide range of loads and generation, like PV and battery, wind, connected through power electronics. And so we're able to kind of, we call it emulate, because there's real power flow, the behavior of the electric grid when we have a high penetration of renewables, and we define that as 80%. And so we've built a clustered generation and load model of the West, Texas, and the East. And the East is simulated in a real-time digital simulator. And we've connected it all with a multi-terminal HVDC overlay, and just look at how can we control the grid of the future, especially when there's things like loss of generation, faults, and that kind of thing. So we've had a lot of good results with this test bed, and we plan to use it quite a bit in the future. So we also, just in general here in power electronics, we've got 5 faculty, including myself. We work very closely with nearby Oak Ridge National Laboratory, who also has a large power electronics research related to electric vehicles or the electric grid. We have a traineeship I'll talk more about called Potential, which is specifically for wide bandgap. And we work with several companies, including ABB and Boeing, GE, Intel, Volkswagen. So our wide bandgap traineeship program is now 5 years old. It was to encourage more students to pursue working with wide bandgap devices. And so far we've had 28 students, and starting this fall, there'll probably be about 4 or 5 more students. So we'll have more than 30 that have participated. And you can get more information about this and in most things in terms of papers and students and classwork at this website here, Potential, spelled with 2 N's, eecs.utk.edu. Our power electronics research spans a wide variety, as mentioned in the introduction today, anywhere from consumer electronics and medical devices and data center power supplies, things like microgrid, electric vehicle, aerospace, and then the utility applications in renewable energy. Today I'll be talking mostly about a 10 kilovolt silicon carbide devices and building a phase lag and converters with those. And so that's most likely going to impact these areas here. Utility applications, of course, and the interface with renewable energy could also impact electric vehicles. Things like fast chargers, electric vehicle chargers would also likely use 10 kilovolt devices or higher voltage to try to minimize the amount of current needed and drawn from the utility. So this is an outline of the talk that I plan to give today. We're going to first talk about some of the switching performance evaluation, kind of an overview of what we hope to accomplish testing these 10 kilovolt silicon carbide MOSFETs. We're going to talk about the design that was done using these devices in a phase lag. We will also discuss the impact of parasitic capacitance on switching performance, as well as the impact of the body diode and anti-parallel Schottky diode that was added, and see how does that affect the switching performance. And then just kind of have a short discussion on some of the gate drive and protection issues that you need to consider when evaluating these 10 kilovolt devices. So, as I mentioned, 10 kilovolt devices are going to be needed if we start looking at medium voltage converters. There are several applications where these are used, things like offshore drilling platforms or offshore wind turbines and things like that. I already mentioned the fast charging applications. They could also be used on the front end of data centers and things like that, or electric ships is another area where we're going to see use of these very high voltage rating devices. Most of them today, of course, are using IGBTs, but I think as we see, IGBTs are minority carrier injection devices, which means they don't switch quite as fast because you have to inject these carriers in before you can get conductivity modulation. And so IGBTs kind of have a limited switching frequency, especially the higher voltage rating devices, just a few kilohertz, typically are only used at 1 or 2 kilohertz when you have the really high voltage devices. I think most of the people in this seminar are familiar with wide bandgap devices, and as you can see here, there's I'm trying to minimize something on my screen here. Let me see if I can do that in just a second. Oops. Okay. Hopefully everybody can still see me. If not, speak up. So this here is showing the comparison between silicon carbide, and gallium nitride for several different things. And as we can see, silicon carbide in particular has a wider energy gap than silicon. Electron velocity is also higher than silicon. It's got higher thermal conductivity than silicon. And so that likely means we're going to be able to use these at higher voltage and higher switching frequency. And that is going to be what hopefully leads to higher efficiency and switching frequency when we use these devices. So 10 kilovolt silicon carbide MOSFETs have been produced by Cree or Wolfspeed. They're now on to their third, working on their fourth generation. And so we've been able to get a few of these devices and build some converters with these. Some of the benefits I just mentioned about 10 kilovolt silicon carbide MOSFET is that higher voltage, higher switching speed, higher operating temperature, and higher switching frequency. And these two things, some think, well, aren't they the same? Higher switching speed and higher switching frequency? Not exactly. Switching speed means how fast it can transition from on to off or off to on. Switching frequency, of course, is how many times are you switching in a cycle. Certainly, if you can switch it more quickly, that typically allows you to switch it many more times per cycle, but you don't necessarily have to. These device benefits, of course, lead to several converter level benefits like simpler topology. Perhaps we don't need multi-level converters or not as many levels in our multi-level converters. Hopefully leads to higher efficiency. If we can switch it faster, the switching loss should be less. If we can do higher switching frequency, typically that means our passives and filters can be smaller. And hopefully that also leads to a higher control bandwidth. And some of the challenges associated with this. So a lot of times we said, oh, we would like higher blocking voltage, switch faster, and higher temperature. However, you have to be able to accommodate all of these things. And so this faster switching typically leads to stronger noise or higher EMI if you're not careful. It also causes more risk to insulation failure. Those transients, that very fast switching, can lead to higher DVDT, DIDT, which are sensitive to parasitics, so we have to be more careful there. It also typically requires more comprehensive testing. And typically a higher current density means we have a less short circuit withstand capability. So some of the benefits and challenges here specifically related to 10 kilovolt silicon carbide MOSFETs. One has to do with the reduction in switching loss. If we look at the turn-on energy, you can see silicon carbide MOSFET is 136 millijoules, 19 at this lower voltage, comparable to a silicon IGBT, which is more than 10 times and closer to 20 times higher. Same thing for turn off. You can see here that for the silicon carbide MOSFET, the turn off is much less than a silicon IGBT. And then if you just look at the sum of the two, again, a reduction by about 20 for a comparable, at the comparable voltage for the silicon carbide MOSFET compared to the silicon IGBT. So that's an illustration of the benefit, meaning this much less switching loss. However, if you start looking at the flip side of that, which is that very fast switching, that very high DVDT, DIDT, you can see down here the silicon carbide MOSFET is on the order of 20 volts per nanosecond, whereas the silicon IGBT is more in that 4 to 5 volts per nanosecond, so about a factor of 5 less. Turn off, even faster here for our silicon carbide MOSFET, And silicon, as we know, their turn-off is not so great, and so it's slower here. But that means we have to be able to withstand this sort of very fast dV/dt in our circuits and make sure that our parasitics aren't such that we're going to end up with an overvoltage somewhere. And similar here with the dI/dt, you can see the rise time about an amp per nanosecond for the silicon carbide MOSFET, whereas for silicon it's maybe 1/4 of that, so much less. So one of the things that we wanted to look at was the switching performance evaluation of these devices and understand those switching transients and be able to do that switching loss estimation. And so a common method used for testing devices is called the double pulse test. This is showing a typical double pulse test setup where your tested device is here. Typically you have an inductor here to allow a continuous current and a freewheeling device such that if you turn this off, there's a path for that current to freewheel up here. And then when you turn this on, there's a path for that current to flow here, and a DC power supply. Many things we want to look at, like that dV/dt, dI/dt, that switching energy. We do want to look at voltage overshoot and things like that when we're doing this device testing. So for a half-bridge phase leg that's based on 10 kilovolt silicon carbide MOSFETs, you can see this is a typical phase leg where you just have two switches in series connected to your DC link, which typically has some capacitance in it. We have, of course, what's referred to as the upper switch, lower switch, and your switch node. Typically in three-phase applications, you're going to have three of these all in parallel. Many times there's an anti-parallel diode. Of course, that could either be the inherent diode that's within the device itself, or it could be a diode that you've added. And so one of the things that we looked at was, do you need to add a diode, or can we just use that inherent built-in diode? We also looked at the effects of heatsink and how does that affect things. And we looked at the parasitics. Parasitics, particularly parasitic capacitance, is something that comes into play at this very high voltage devices and very high dI/dt. That's something we typically don't think as much about at lower voltage devices, the 1200 volt devices. We worry about the parasitic inductance, but we don't typically worry quite as much about parasitic capacitance. But we do when we have these high voltage devices. So down here is just kind of illustrating we're going to worry about some of this parasitic capacitance that could be in the load, could be between our devices and the heat sink itself, could also be related to if we added an external diode here, could be related to that external diode. And so this will be something that we explore a little bit later in this talk. That's what I'm referring to here about adding that external diode. So switching loss in these high voltage MOSFETs, typically their turn on is going to be mostly controlled by your gate driver. Are you able to provide sufficient gate current and voltage and keep it at a fairly high current and voltage? And if so, you can turn it on pretty quickly. Turn off is more dominated by that being able to discharge the device and how quickly can you do that. Some of the things that we're going to look at are things like gate resistance, temperature, voltage, and current. We also looked at junction temperature. We found that at least for the turn-on transient, there was not a whole lot of impact there. typically, a lot of times when people are doing these double pulse tests, they're just kind of testing a single device, and they're just maybe not even mounting it on a heat sink. And so one of the things that at least we want to advocate is that while it gives you some indication of how that device switches and its behavior, it's not all that predictive or indicative of its behavior when you actually put it into a circuit. And so if you really want to know how something behaves in a circuit, well, you need to build the circuit. And so we're kind of advocating, if you want to do this sort of a testing, for instance, know how well is this device going to switch in a motor drive, well, you need to build the motor drive, or at least as a minimum build one phase leg of that motor drive. And so that's just something that at least I want to advocate, is while it double pulse test gives you a little bit indication of how it'll behave, a much better indication is actually building the circuit itself. So this on the right is showing things like the switching energy as it relates to gate resistance. And of course, if you increase that gate resistance, typically that means you're slowing down that transition. And so that's going to increase that turn-on loss because you're slowed down that turn-on time. It's a longer turn-on time. And that, of course, then leads to that higher energy. This is showing tested at 7 kilovolts, 15 amps, looking at different gate resistance. The bottom is showing for a fixed gate resistance of 20, and then looking at how does the different current affect. And you can see that higher current is going to lead to higher turn-on energy loss, because again, it's going to be that product of how much current you're trying to carry through that device. But notice the turn off is not really a function of how much current goes through it. As I mentioned, some of the challenges are this high voltage and high DVDT. Crosstalk, something I talked about in the lecture that I gave in January. You can do something like active Miller clamping to limit that. This was something, at least with our 10 kilovolt phase leg, that we did not have to worry about as much. So this was something that really didn't affect us as much as it did when we looked at the 1200 volt. And I'll talk more about that in a minute. Overcurrent protection, very important that you don't damage these devices. These particularly 10 kilovolt devices are few and far between, very hard to get your hands on, and so we don't want to damage any of these during testing if we can avoid it. So we did want to make sure we had proper protection. And so we wanted to monitor our gate driver and some of our communication to make sure that when we had a PWM signal, it was actually making it all the way to the gate here. I'll talk more about this too later. Some of the things related to overcurrent protection, you want short response time, of course. You want it to be as quick as it can be, but you don't want it to respond to something that's not a real event. So you do want to build in some noise immunity, which typically means you need some blanking time. And it needs to be something that's not that hard to implement. Typically, Desat protection is a very common protection method used to protect power electronics, where you just monitor the voltage across the device. And if it gets to be above a threshold, then you shut it down. And so that is something that we used. However, we didn't just set a constant threshold current. We tried to change that current with temperature or with load so that it could work well. We did use a Rogowski coil, which seemed to work okay. However, when we tried that, we found that its response time, while being short, the design was not so great. Freewheeling diode, again, I kind of alluded to the fact that maybe you can just use its own body diode in these devices, although we did want to see what happens if you add an anti-parallel diode. We actually found that body diode is pretty good, and as you'll see later, that we essentially did not need to add this extra diode like you typically do in many applications. At least with these 10 kilovolt silicon carbide MOSFETs, we found that's something you do not want to do. I'll talk more about that here in just a second. So this was kind of our device test plan. We wanted, as I mentioned, to look at several factors. Here's the things that we wanted to do: Desat protection based on a Rogowski coil, and then look at some other things. And we wanted to look at that freewheeling diode and its impact. So the next several sections here are going to look at some of these test setups and how this all worked. So this here at the bottom is a 3D design of our phase leg, where basically we've got two 10 kilovolt silicon carbide MOSFETs. Here you can see the capacitors are taking up a substantial area. These are the power supplies that are used for the gate drive. Here on the right is showing that architecture of that phase leg, where you have some PWM input, you have your gate driver. We also had a feedback signal. As I indicated, this feedback signal is kind of to let us know, is our device still switching? You know, is it actually turning on, turning off? We thought this was important to kind of keep up with our things working like how we should. We'll talk a little bit more about that here in just a second. And much of our tests were done at 6.5 kilovolts. So a 10 kilovolt device, you don't want to use it at 10 kilovolts because typically any kind of overvoltage will damage it. So we derated and used it at about 6.5 kV. So our spec was to, again, use it at 6.5 kV. We designed to accommodate about an 80 volt per nanosecond DVDT. Our driving voltage was about 20 volts with a -5 for the off. Typically, -5 to 15 worked fine, so we didn't need to try to push it up to 20. So this is what we ended up doing. Our gate drive was about a 9 amps in the gate drive itself. You can see rise time, fall times, about 22 nanosecond rise time, 15 nanosecond fall time. Our short circuit protection, based on looking at some of the withstand capability of these 10 kV, 20 amp devices, we wanted to be less than 1.5 microsecond. And so we ended up about 1.3 microseconds. So down here, this block diagram is kind of showing, again, all the things that you need to put together. You have your typical gate drive, but there also needs to be some protection that can turn that off in case you detect an issue here. As we mentioned, we're using Desat protection, which means we're monitoring the drain to source voltage. If it gets to be too high, then we take some action to turn this off. As I mentioned too, there's a feedback signal. Basically, if we detect a fault, we want to send that back and let the controller know that there's an issue there. There's a need for dead time. to make sure that noise is not influencing things and we don't turn things off when we shouldn't. So just to, again, look a little bit more at this feedback signal and how that is. So typically, your initial gate signal is shown here in blue, and then there's a little bit of delay to acknowledge that every time you have a rise time or fall time. And so that ends up setting up something like this. And then we have if you had a high fault signal, meaning that something occurred, we want to be able to report that. And then if there is an actual change in that fault signal here, which is showing, okay, you've got a real fault, then you get some sort of a feedback signal here where you're getting a pulse that would not be at the normal place when you're getting your normal pulse. And so this would be an indication that something's happened here. Typically, that status feedback signal, of course, is going to add a little bit of overhead to your controller. You could see here that it required about 4% of our duty cycle if our switching frequency was at 80 kilohertz. And so a 10 kilovolt device switching at 80 kilohertz, most likely you're not going to be switching it that fast. So I think this was something that we could accommodate. And this typically having that 500 nanoseconds during switching of blanking time, what provided sufficient noise immunity. Gate driving stage, I mentioned the voltages that we used. Here we used a 15 ohm for the turn on, 3 ohm for the turn off. I mentioned too that the anti-crosstalk circuitry not really necessary for these devices, mostly because they have such large capacitance, gate to source, gate to drain, and so that was something that we did not have to accommodate or worry about. This is showing some of the different gate drives, commercial gate drives that we considered, kind of a comparison of those. You can see we settled on this one from Ixis. It seemed to, in terms of propagation delay, rise time, fall time, and mostly it had a fairly good peak current capability, kind of fit with what we were needing. Additional comment about that overcurrent protection stage. It needs to be able to protect against several different faults, fault under load, hard switch fault, and also any other faults that you might have. So this was something that we also wanted to make sure had high noise immunity. We also wanted that threshold current to be a little bit higher at lower temperature, meaning at low temp you can withstand more fault current because it takes a while for your device temperature to rise if it's starting at a lower temperature. And we don't want that diode to necessarily be affected by high voltages. So our threshold current, at least our triggering current, was 20 amps at 125 degrees C because we have a 20 amp device. But then we increased that current to 40 amps at a lower temperature. The other thing you also have to be careful in overcurrent protection is that you don't just turn it off. You have a very high current and you turn it off too quickly, that can lead to over voltage and damaging your device. And this was something I talked about in January with the 1200 volt silicon carbide MOSFET. also very true with these 10 kilovolt devices, that we have to do what's called soft turn off. And so here, instead of using that 3 ohm gate resistor, we have a much larger gate resistance when we're turning it off if we detect a fault. And so that soft turn off, or slow turn off might be a better word, allows us to make sure we don't end up with an overvoltage. And again, the ratings of everything have to be very high. You can see a 10 kilovolt to accommodate that 10 kilovolt device. This was just showing some of the IV characteristics of that device. And you can see here that at different temperatures, you know, at low temp, you can have a higher drain current than you do here, down here at higher temperature. A few more details on the Desat protection. This is showing here, put several diodes in series, you know, to accommodate that 10 kilovolts. We didn't have a 10 kilovolt diode, so we put 4 3.3 kilovolt diodes here. We also needed some blanking time so that we don't, again, have false triggering during the turn on. We figure we needed more than 500 nanoseconds, so we ended up with about a 600 nanosecond blanking time. And so we ended up, in addition to that minimum blanking time, we ended up with about 1.22 microsecond blanking time that we used. You can change it if you want, of course. If you want a shorter response time, you just can change your RC circuit and change that as you see fit. This here is showing a turn-on transient. You can see initially blocking a substantial voltage, and then as the device turns on, you can see the rise of your gate source voltage. You can see the rise of your drain current. You can see that your current actually does have some overshoot there as you turn it on and as our voltage is falling down. And what we're essentially saying is that you do not want your protection to activate during turn on. And so because this overcurrent as you turn it on, so that's why you need that blanking time. You kind of want that turn on event to occur and then check and see if you still have some high current, or you have high current later, then that would indicate you have a fault. Just turning the device on should not indicate you have a fault. So that's why you need at least blanking time during this switching period. And so, you know, once we built this phase leg, which is shown on the right in hardware, we want to make sure that we do a fairly comprehensive test of it, and that test needs to be a non-destructive test. You don't want to damage it, even when you're trying to do these short circuit tests. You hope that the hard switch fault under load, that those don't damage the device. And then later we wanted to, of course, do some continuous testing, not just a double pulse test, but where you're actually switching, conducting, and providing power to a load. So these are kind of some steps where we were very deliberate, trying to do, you know, make sure all of the connections checked out, that our gate drive functions were working properly. This is before you even connect it up to the device itself. The second thing we did was do quite a bit of double pulse testing to kind of check how is that device working and whatnot. Then we moved into our short circuit tests and did quite a bit of those tests. And then finally, some continuous tests. As I mentioned, we want to operate it continuously. And so you don't want to jump ahead in this testing sequence, build something and just, hey, let's go see if it works, of course. And so my message again to students and others is to be very methodical when using these very high voltage devices in your testing and whatnot. And be very slow, be planned, check things out, and hopefully your results will be much better doing that. So some of these short circuit tests for that phase leg, the worst case for the Desat in terms of response time was the hard switch fault, meaning that the fault occurred as you turned it on, mainly because, right, we had that initial blinking time, and so we're doing nothing when we turned it on, and then but that current continues to rise. And so instead of it going up and then coming down, that current just continued to rise. And then after that blinking time is over, we say, oh, there's something going on. We have a fault. We need to turn it off. And this is showing how that gate voltage then is then brought down. Our drain current, as we turn it off, comes down. It's not so steep, you know, that softer turn off here. And our voltage, again, then goes back up. And this is showing just a couple of different tests. One was with the lower MOSFET in the phase leg. One was with the upper MOSFET in the phase leg. And so again, if you're testing a phase leg, it's important to test not just the upper or just the lower. You need to test both and make sure they're behaving. And you can see they behaved fairly similarly, about 1.2 microseconds response time. Of course, this was at 25 degrees C for the device. Continuous testing. This was where we were wanting just to continue switching and see how everything looks. Make sure there's no issues here. When we looked at evaluate to see if there was some crosstalk, meaning does the switching of this device affect the gate drive or this device or vice versa. You can see a little bit of noise here in the opposite device when one device was switched, but not too much. So that's why we refer to that as very slight crosstalk. But again, it's something you want to evaluate and make sure that switching of one device does not affect the other. And then this is just a thermal camera photo of our device and showing that it was running, about 50 degrees at the hottest temperature somewhere in here. Not too bad. So again, at least just kind of a summary of that phase leg testing. We were able to develop a Desat protection scheme, typically could switch less than 1.3 microseconds. And we had very systematic procedures to test that phase leg and make sure there was no damage. Okay, as promised, we wanted to look at what were some of the impacts of parasitic capacitances on the switching performance. So this next section of the talk is going to be about that particular aspect. As mentioned, parasitic capacitance could be from several different sources. You could have some in the load itself. You could have some in the, if you added a diode here, there's parasitic capacitance just between the devices and the heat sink. And we found that there's actually some consideration that needs to be taken for that. And so, again, this is something a little bit unique when you're looking at these medium voltage converters, and something that perhaps you don't typically look at lower voltage converters. But because of this very high voltage, parasitic capacitance ends up becoming more of an issue. And so this is just showing a few more details of the double pulse test setup. Part of our setup was to use large inductors as loads. That inductor had a parasitic effective parallel capacitance of about 35 picofarads. Over here is showing some of the setup and some of the measurements that were done, some of the current probes and external capacitor. You could just add some extra capacitance if you wanted to. This was basically the bus bar is in the printed circuit board and the capacitors are connected underneath. Notice some things like Kelvin connection, also important and used in our test setup here. So that larger effective parallel capacitance in that load inductor slows down your turn on and turn off because you're charging and discharging that external capacitance. And so that charging and discharging of that capacitance, the larger the capacitor, that typically means that our dV/dt is going to be less or slow down. So the solid line is our turn off, the dashed line here is our turn on. And so that slower, longer or slower dV/dt, you know, that's going to end up increasing your switching loss, basically. And so this is something that you would not learn if you did just a double pulse test without a load, because, you know, this is the load itself affecting the device and how fast it can switch. As I mentioned, that did affect our turn on and turn off loss. You can see here that the larger capacitor that in that load had the higher turn on loss. Not so much of an effect on the turn off loss, though. You can see not too big of an effect. It's more related to the turn on. And you can see here that dash is that larger capacitor, and your turn on transient is slower. You can see your ramp up is slower when you have that larger capacitance. Turn off, again, not a whole lot of difference. And that's all related to, again, that capacitance that's in your load. And so if you just look at total switching loss, you can see there's an increase. It's not a huge increase, but it is an increase on the order of 11 to 16%. So in terms of going from here to here, yeah, about an increase of 15% switching energy loss when you have that capacitance in your load. If you looked at switching transients, which I showed you the difference there, this is with no external capacitor and showing how that drain source voltage rises, and then this is showing without it. You can see the turn off transient, it's quite a bit different. And then here is showing, this was with 4 amp and this is showing with 20 amp and showing that difference. Unfortunately, here the dash is with the external cap, and here the solid is with the larger capacitance. Okay, shifting now from the load to looking at what about the capacitance in the heatsink. So we looked at a couple of different designs. One design was where each device in the phase leg had its own heatsink, and we called that thermal design A. And then we looked at thermal design B, where you had just one large heatsink and both devices connected to it. Again, this is kind of the traditional way of doing things. You typically just want one large block heatsink and put all your devices on it. However, what we found is at least this larger heatsink, that effective plane basically leads to a larger effective capacitance between that and the devices themselves. So let's look at the differences here between thermal design A, which is separate, and thermal design B, which means one large heatsink here. Also, this heatsink is grounded, whereas these two heat sinks are floating or not grounded. So looking here at the turn-on energy loss, the solid line is A, the dashed line is B. The turn-on, there's really no difference. But notice in the turn-off, at least, the design B, which is the large heatsink, actually has quite a bit more loss, turn-off loss, due to that capacitance in that heatsink. So we can see at least that the heatsink design is going to affect your turn-off loss, not so much your turn-on. Again, it's not necessarily a huge amount, but it's, you know, on the order of 5%, 15%. Something that you may want to consider. And then we wanted to just look at what about a capacitance here on the device itself. And of course the device has some internal capacitance, but what if, you know, you adding some capacitance here? And you can see that adding that capacitance directly across the device is going to increase quite a bit your switching loss, because it's going to slow things down, both the turn on and the turn off. So going with that, it just adds quite a bit of extra loss here. So that larger capacitance in your load inductor is going to make your transient slower. It's also going to affect things like DVDT, but typically it reduces that, and so it's something you don't have to worry quite as much about. You do need to think about your heatsink design with these devices and whether you're going to ground it, whether you're going to not ground it. Are you going to put separate ones? Are you going to use one large heatsink? So just, I call additional things we need to worry about with these 10 kilovolt devices. Okay, next we're going to look at the body diode and how does that affect our switching performance. And should we add this anti-parallel diode? And I've already kind of given you a preview and said most likely we do not need that. So this is again showing our device under test. This is showing here basically the 10 kilovolt MOSFET is underneath our interface board. There's some decoupling caps here. And we looked at 3 different configurations. We looked at one configuration where we basically added a freewheeling diode, and then we also had this diode in series. Configuration B, we added a freewheeling diode, but we do not have that diode in series. And configuration C was just the body diode. We did not necessarily add an additional diode there. So all of them, they have, of course, its own built-in body diode. We added these two, B, we added this diode. And this again is just looking at with that anti-parallel diode and characterizing. You can see that with the dash is the body diode and the solid is that other diode. And everybody says, well, you know, that extra diode, it looks better than that body diode in terms of it just as a diode as itself and its current capability, but we're going to find that it ends up adding quite a bit of additional parasitic capacitance, which is not a good thing. There's, you know, negligible reverse recovery in that body diode in this silicon carbide. So unlike silicon devices where you have to worry about reverse recovery, I think you've heard a lot of people talk about we do not worry about reverse recovery with silicon carbide. And that's true with these 10 kilovolt devices as well. There's essentially no minority carrier injection. And so just looking at it, you know, it's not something you need to worry about in terms of switching. So looking at the impact of the body diode, first we're going to look at configuration C, meaning that's just the body diode and we're not adding these additional things. You can see here this is the turn off behavior and the turn on behavior, and you can see what that looks like in terms of dV/dt with respect to temperature. You can see that the turn off, not much of an effect in terms of temperature, but the turn on, there is an effect. If we look down here, you can see the solid line is configuration A, and the dashed line is configuration B. And this is showing that switching behavior of basically this is on the left side, the turn off. On the right side is the turn on. You can see quite a bit of current overshoot here. And so that is something that we need to worry about. So adding that diode does increase our switching loss, particularly the turn-off loss. You know, we compared configuration B, configuration C, and it showed that diode could be modeled by a nonlinear capacitor, basically, if you wanted to model it in simulation. Hear quite a bit of background noise. Sounds like somebody needs to turn off their mic. There we go. And slower turn-off transient, higher turn-off loss, basically when you have that additional diode there. And just looking, solid line is configuration B, dashed line is configuration C, which is where we don't have it. You can see it just faster rise time without that diode, slower rise time. 58.5 volts per nanosecond without that additional diode, and about 49 volts per nanosecond with that diode. So that's illustrating the difference there between B and C. You can see on this end, the turn on, no, it's not a whole lot of difference. So it's more on the turn off. So adding that anti-parallel diode, you know, increases the turn-off loss some, and it's mostly because of that energy stored in the capacitor of that extra diode that you're adding. And so this is then showing what it looks like in terms of the switching loss with that diode and then without that diode. And you can see that the turn-on loss is about the same with and without, but you can see the turn off, these two, you can see quite a bit of difference here, quite a bit higher with that diode and compared to without. And then this is just showing the increase, or that delta, how much added turn-off loss increase at these different temperatures, test temperatures, because of that capacitance in that extra diode. So as a summary of that, the body diode basically has very little reverse recovery, and you don't necessarily want to add an anti-parallel diode. It introduces some parasitic capacitance to increase the switching loss. So at least our recommendation is to try to use that built-in JBS diode. And so just a few more comments here related to some of the things that we did in terms of some things that you need to think about, particularly for high voltage devices. You do need a isolated power supply, and a lot of times, you know, that's transformer based. You want all of your signals to be isolated. That means you're going to be typically using things like fiber optics, gate drivers, either a totem pole circuit or using gate resistor, and you need quite a bit of protection as well. Insulation requirements, very important. You have to worry about these voltages and edges and not having sharp edges and things. You want to make sure that you have an accurate gate drive voltage that's load independent. We talked about making sure you have low coupling capacitances and things like that. We typically need very fast switching speed because we have such a high voltage that has to rise in a long time. This is kind of summarizing again some of those things that we looked at earlier in terms of gate drive voltages and currents and rise and fall time. Overcurrent protection stage also require just kind of a summary that response time needs to be pretty fast, but at the same time you need blanking time during turn on. You need this soft turn off. May need some current boost for your gate drive to help with that turn on in particular. And so sometimes you need not just that 5 or 10 amps, but in this case here, you may need to generate something like 80 amp boost current to make sure things can turn on more quickly. Protection, that Desat protection, as I mentioned, seems to work pretty well. But again, you have to make sure things are rated for the voltage that's needed. So you may have to put several devices in series to reach the voltage level that's needed. Typically, it needs to be temperature dependent. A lot of times we want things temperature independent, but this is a case where at low temperature, you want to allow higher current before you take some action. And at higher temperature, you want it to be quicker. And I mentioned the blanking time. Certainly noise immunity, as we talked about. Main concern is that high dV/dt, and so you need to be sure to build in noise immunity into your Desat. Blanking capacitor, as we mentioned, this is to make sure that things don't take place during switching, so you need to build in a sufficient blanking time. I want to take a little bit more time to talk about this. This is something that's maybe some folks aren't aware of when we were looking at this, but when you're using these high voltage silicon carbide MOSFETs, I kept talking about we have a very high dV/dt. Not only do we have a high dV/dt, but we have a long voltage rise time. And you're saying, well, that doesn't make sense. If it's a high dV/dt, it should be fast, meaning that the time should be short. But if you have a high voltage device that's like 10 kilovolts operating at 6.5 kilovolt, well, that takes a long time to go from 0 kilovolts all the way up to 6.5 kilovolts. So you have to be able to withstand a high dV/dt for quite a few nanoseconds. And so this region here in this dV/dt and just voltage rise time is something we don't see in other devices. We don't see this with silicon IGBT. They also have a long rise time, but they're not so fast. With our silicon carbide MOSFET lower voltage devices, they're very fast, but they're at lower voltages, so they're not so long. And so this is something I kind of wanted to highlight here, and something of concern that we see with these 10 kilovolt silicon carbide MOSFETs that you need to design for, be prepared for, that you don't see with your low voltage devices or your high voltage silicon devices. Again, we need improved noise immunity. That typically means our power supply, you want it to typically have a higher voltage so that this low voltage noise doesn't affect it as much. Again, a higher input voltage. Typically a longer delay, again, so that noise not going to affect it as much. But that means your Desat protection is going to also be delayed. Typically a little bit higher threshold voltage as well. So these are just kind of some tips when you're designing that Desat protection to improve noise immunity. And typically, if you can suppress that voltage spike, that's going to give you larger voltage margin. Some of the things that you can do there is to reduce the capacitive coupling, reduce the clamping resistance, reduce that voltage divider impedance, increase CD. And so this is showing some of that Desat protection circuit and just kind of a summary of some things that you can do to improve your noise immunity. Showing how reducing voltage reduces your voltage spike. This is again showing how reducing that resistance also reduces your voltage spike. Also, you can add some, we refer to as a digital blanking time from your controller, can also allow improved Desat protection. I kind of talked about this earlier, but again, just adding that blanking time also helps to have better noise immunity. Response time for hard switch fault is typically determined by that digital blanking time because you're switching into a fault and it rises very quickly, but if that's during your blanking time, and so once that blanking time ends, you're going to detect that fault immediately. One thing I'm not talking about today, because I guess we haven't published those results yet, is flashover fault. This is also something unique to 10 kilovolt devices and something that is of concern that you don't worry about with your low voltage 1200 volt or even 1700 volt. So while you're talking about worrying about hard switch fault, fault under load, flashover fault is something that you need to worry about. with these 10 kilovolt devices. And so that's, I call it almost a whole separate issue. And so we should have a paper coming on this topic to talk about flashover fault with 10 kilovolt devices. And so, again, just looking at improved DSAT protection means if we took, I call our own advice, and went through and changed some of the capacitance values, changed some of our resistance values, and basically we were able to have a fairly fast response time, 340 nanoseconds for a hard switch fault, 195 nanoseconds for a fault under load. So that's a very, very good response for these kind of devices. Very quick. And so just kind of a summary. This slide is a good summary of the DSAT noise immunity summary. What can be done if you reduce your capacitance? Basically, there's always a trade-off, though. That's something I think, again, as students and we as application engineers learn is there's always a trade-off in all of these things. And typically by making parasitics low and whatnot, that may end up increasing our cost and size of our layout. We need to reduce our LDSAT. Again, that has to do with PCB layout. Adding this resistance, just a little bit higher RDAMP. There's a couple of things you may want to reduce. Of course, that may it may help with your noise immunity, but it may also give you slower response, maybe a little bit higher loss. So that's always your trade-off, better noise immunity, but it's going to be slower to respond and that kind of thing. But with that improved device, again, very good response rate. But like I mentioned, flashover fault is another thing that needs to be considered. Current sensor, this is showing the design of that. We're basically designed, I call it a Rogowski coil, and implemented it in the printed circuit board is something that could be done. So just to draw a few conclusions, parasitic capacitances is something that increase our switching loss. They slow down that switching transient, reduce DVDT, but not necessarily the peak DVDT. Also, anti-parallel diode, adding those add capacitance. And so it's not recommended to add those. Flashover fault, you can experience very fast transients and disturbances. And so those faults are actually worse than FUL and hard switch faults. And the high DVDT has a long duration with these high voltage devices. And so it makes them more susceptible to noise. And so that's something that you really need to spend a lot of effort with your DSAT protection and whatnot to make sure it's more immune to noise and whatnot. And then we talked in general, just some of the things that you need to consider when you're using these very high voltage devices. Here's several publications that our group has had for the last few years. Most of these are fairly recent, 2018-19. We had several planned for APEC last year, which of course got canceled, but they are available from IEEE Explorer. And then these are a few references of some work that some other people have done. I know there's been quite a bit of good work done at places like North Carolina State, Virginia Tech, ETH, and several others. So several other people are also working on this topic as well. wanted to acknowledge that, you know, there's many students that worked on this work and did this, so, and other faculty as well. So I wanted to acknowledge all of these folks. So thank you. Let me see if I can click that and be happy to answer questions.
Yes, thank you very much, Professor Tolbert.